Good morning, mathematicians. Welcome to a new day. We're really getting into this week. I guess some of you started spring courses today, or not today, but this week. Gotta like my own stream here. We haven't looked at Reddit for a while for math news. Um, so maybe we should do that today. And then keep talking about the algebras. I don't know. Also, let me know your course ended. I guess your winter course, right? Mind you, I guess semesters work differently in different places. Where I am, the spring semester, the winter semester just ended, and the spring semester is about to begin. I don't know why my eyes are so dry right now. Probably because this place is dry. You do fall, spring. Okay. Yeah, I see. Yeah, we have. So I think maybe what your spring is what we call um, winter, because winter is a significant chunk of the year here. So we have fall, winter, are like the normal semesters. Oh, moving to start your masters. That's exciting. That's exciting. Congratulations. That's fantastic. Or maybe I should say my condolences, because that means you're an addict like the rest of us, hanging out here on a Wednesday morning to talk math on YouTube. Let's see. Reference request. Is this a hidden dunk on reference request for treatment of differential geometry, which is elegant or beautiful, implying that they've seen a bunch of differential geometry, which is not elegant or beautiful. Um, hmm. Wait. I've surprised myself a bit when it comes to my studies of mathematics, and I've wandered very far from what I would call applied math into the realm of pure math. Yeah. It is so funny. Where was I? It's so funny when you're at a yeah, I was at a conference this weekend, and someone asked about the applications of some result, and of course, this is a number theory conference, right? So I don't know. You go other places, and people, someone asks applications, and of course, you're thinking that, oh, maybe some sort of real world applications, but no, of course, the person asking this question means, like, oh, what kind of like number fields can this be applied to? And yeah, I don't know. Well, the course is at Bonn. Oh, you're going to Bonn. Wow. Congratulations. Or yeah, I guess condolences. Condolences. Um, but hey, I mean, that's great. Um, um, you'll probably learn a lot. You'll probably learn a lot if you're at Bonn, and if your courses are brutal. I mean, this is the thing. I've said this before. People complain about courses being hard. Um, but I don't know. Yeah, I've had courses that are hard. I've had courses where you could make an argument that the instructor was too harsh, but I just never felt like I've never complained about the difficulty of a course. Um, Maybe the way that someone conducted themselves, but the difficulty. I mean, honestly, thinking back on all the courses that were the hardest, those were the ones that I learned the most from, were the ones that pushed me more. So, um, yeah. Um, have you ever seen a math textbook and thought to yourself, hard to believe more than 30 people can understand this? Kind of. Um, Motivic integration. Okay, yeah. Yeah, that's definitely one you look at and you're like, yeah, who understands this? A library exclusive to a bunch of math books, which are completely meaningless to me. Yeah, yeah. A topic called motivic integration. Uh-huh. Oh, since you're studying Lebesgue, yeah. I mean, especially if you got to the topic of motivic integration, because uh, by way of Lebesgue and probability theory, yeah, you're just gonna get wrecked from page one. Um, yeah, yeah. I know nothing. I mean, I know next to nothing. It actually is related to there's um it's definitely related to stuff in my work. Um, you're doing sort of weird. Wow, Wikipedia really dropped the ball on this one. Yeah, I've never learned much about it properly, but there's like a chapter on it. There's like these Ottawa lectures. Actually, I think Julia Gordon wrote the chapter in the Ottawa lectures on the Langlands program, um, who came to visit my group not too long ago and gave a talk. There's a lot of topics in math that you imagine even people who have taken sufficiently many grad level courses in math would have to sit down and try to figure out what the particular topic is. Yeah, well, yeah. I guess it depends on what you mean by figure it out. I mean, you know, normally the introduction to a textbook will have something, but yeah, I mean, if you toss an arbitrary theorem in front of someone and be like, yeah, go ahead and um, oh look, yeah, there we go, Julia Gordon, an overview of arithmetic motivic integration. Nice. Karen Smith. Oh, algebraic geometer. Oh, and Tom Hales. Okay. Um, yeah, but also the NLab page is not great either. There really isn't much going on here. Disappointing. I don't know. Should we get to some actual math? Maybe we should do some actual math. But what actual math should we do? I know you guys are supposed to have questions for me. Um, oh, this is that is a one image preview of my upcoming video. I'm getting political in a video on Friday. Uh, sort of, but not really. It's either gonna make or break me. I feel like this video is either gonna be really popular. It's like a meme video, but I feel like it's either gonna be really popular or it's gonna turn all of you away from me. Uh, Part of the reason you say it that way is that for advanced topics, there are many aspects of it that's analytic in nature, but the modern development of the theory is different. Analytic number theory. I'm not so sure what you mean by that. Um, yeah. Um, but let's turn back to some representations of SL2. Uh, well, where were we? So I think last time we made the realization of a couple things. So we recognized that in general, if I have some representation of SLNC, it'll act we could on some vector space, or sorry, SL2C. We're not getting that general yet. We could then break this space up in terms of eigenspaces. That is eigenspaces with respect to H. What type of math are we doing? We are doing something called, well, I guess this is Lie theory. Really, this is the representation theory of Lie algebras. But also, by the way, I just made a post on the channel asking people what topics they want to see more videos on. So do let me know. Either here or you can let me know on that post would be even better, because then I have it all collected. So I had a brain fart because I was just realizing as I recorded the new Your Proofs Are Trash video today, I forgot to advertise that I do tutoring as well. But maybe that's fine. I don't have a lot of students right now, and that's probably fine. I probably shouldn't get too many students, at least not for the next couple of weeks. Later in summer, I'll be more free. But do let me know what videos. I mean, I probably will slowly still keep making sheaf videos and my categories of modules videos. There should be one coming out. No, that'll be coming out on Friday. But, when those videos are getting like occasionally, less views than my live streams, sometimes it's like, well, maybe I should gear something a little more general. Still maybe, graduate level, advanced undergraduate mathematics, but okay. So we had these eigenspaces, and we figured out that actually, after cheating a little and looking up Fulton Harris, I feel silly too cheating, because I was like, oh, of course, once I saw the answer, I'm like, right, yeah, that's how you create the highest weight, whatever. But it either looked something like this, or like this, either included 0 or not, but it was just integers, all of the same parity, some unbroken string, symmetric about the origin. So of course H, on each of these subspaces just acts by itself, and then E would always increase the eigenvalue by 2, and F would decrease it by 2. Similar things down here, right? Okay. So great. That gives us, well, there's some more work we would need to do here in general. I mean, we figured out, at least not every representation does this, right? But we found out that if it's irreducible, then it should just be some unbroken string. But we have not yet shown necessarily that these things are irreducible. Sorry if this is off topic. No, don't apologize, because this live stream's all about getting distracted and being off topic. Can I explain in basic terms what representation theory is? Your understanding of algebra is at maybe second year algebra, so Galois theory. Okay, well, then it will be very easy, I think, to explain in terms that make sense. So if you've taken some Galois theory, then that probably means that you already believe that groups are a useful and interesting thing to study. And in particular, you've already seen the usefulness of group actions in particular, right? So classic example of a group action that, well, should mean something to you having experience in Galois theory is, of course, if you have some, say, irreducible polynomial, say, f of x is the minimal polynomial of alpha, say, then, the Galois group of Q adjoin alpha. I guess maybe I shouldn't assume this is Galois. But okay, this automorphism group acts on the set of roots of f of x. Okay, so that you already know, right? But that's like one example of a group action that is particularly useful. But group actions can go either way. By which I mean, so here we're using facts about group actions to tell us about some other thing, right? So it's like if we understand the group, then we can learn information about roots of polynomials and whatnot. But the sort of inverse process might also be true. That is, if I'm trying to study a group, maybe the way I can study that group is to find some set on which it acts. So, for example, the dihedral groups are very easy for us to picture, right? These are just symmetries of n-gons. So you can view this as the n-gon is some set on which the dihedral group acts, and it's very nice because it gives us a visual interpretation for the elements of the dihedral group. Whereas, if I just wrote down some general group, like on these three generators, and BC 7 equals 1, something like this, right? Well, what does this mean? How do I, I want to, say this group comes up out of some calculations I'm doing or something, but like, okay, why? Where does this come from? Who cares? Or maybe, sorry, a better way to put that question is like, how can we understand this group geometrically, right? Because groups are supposed to be symmetries of things. So what is this group the symmetries of? And so really the idea of group actions is really what makes manifest the idea that a group is the symmetries of something. It's in particular the symmetries of some set. Now, of course, we can cook up. It's not so hard in general to just cook up random sets and have groups act on those sets. It's even nicer if those sets have some sort of extra structure. For example, geometric structure. We're very visual creatures. So the question comes up, well, can we cook up, are there sort of nice ways in order to study a group where we can cook up group actions on some sort of geometric object? Well, I would say that there's one kind of mathematics that we understand, and only one kind of mathematics we understand, because difficult problems are simply ones that have not yet been reduced to linear algebra. And linear algebra provides us, well, the amazing tools of linear algebra, but also a geometric interpretation. So we might then ask, can I find an action of a group on a vector space? And because I want to, I want the study of this group to be amenable to the tools of linear algebra, I should ask that this action be linear. So in other words, I'm going to have an action where for all, G, V, alpha, U, G acting on alpha V is alpha times, so alpha is a scalar here, G dot V. And of course, G dot U plus V is equal to G dot U plus G dot V. Another way to phrase this is that, so normally an action, right? A group action is equivalent to simply prescribing a homomorphism from G into the set of bijections, sometimes automorphisms in the category of sets, but homomorphism from G into the bijections on the set X. But now we have this extra structure, so G definitely, so what is the equivalent data here? Well, it should be a homomorphism, yes, into the bijections from V to V, but in particular, these two conditions mean that we want those bijections to be linear. In other words, it's a homomorphism from the group G into the group of invertible linear transformations on the vector space V. And if V is a, say, let's say V is an n-dimensional K vector space, then this is just isomorphic to the n by n matrices valued in the field K. So that's what a representation is. Another way to say it, and this actually gives us another perspective on what a representation is, because, so again, groups, fairly abstract objects, right? I mean, okay, if you write it down in terms of a presentation, generators and relation, well, that's actually like fairly concrete. You can do a lot of computations with that. But of course, there are other groups that arise, like in nature, that are just much more, have much more abstract definitions to begin with. And so how might we probe those? Well, again, matrices are really concrete, right? So if there was some way that we could take, every element of our group and pretend that element was a matrix, or represent that element of the group as a matrix, well, that might be useful. And of course, we would want to do so in a compatible way, right? That is that the element GH, right? It's the result of multiplying together G and H. Whatever matrix that gets associated to, of course, we would like some sort of compatibility of structure. So we would, might ask that the matrix that this of this multiplication of the elements is just the multiplication of the individual matrices representing those elements. But what we've exactly just specified in this condition is that pi is a group homomorphism, from G to the n by n matrices. So, in other words, it literally takes a representation, represents every element of your group as a matrix. So that's what a representation is in the most literal level. But also an important question. I mean, feel free. I'm just rambling at this point. Feel free to drop more questions in chat. But an important question then is also, why is representation theory? Well, I think I already gave a bit of an explanation, right? Hopefully that's pretty plausible. We want to understand groups. Getting a grip on those things means, realizing having some sort of group action. And if you're going to have a group action, it may as well be linear. So you can use the extremely powerful tools of linear algebra. So hopefully that is convincing enough. But so I don't know. Maybe I don't need to say more about it. But it does also go, speaking of Galois theory, so representation, there's a whole industry of trying to understand what are called Galois representations, in particular. What about representations over modules or rings instead of vector spaces? Actually, I haven't studied this so much. For your own understanding, would it suffice to show that the homomorphism extends to an isomorphism if the matrix is invertible? No, that is not true. In fact, the matrix will always be invertible because we're taking it. So GLN is the collection of n by n invertible matrices. So they'll always be invertible, and in general, this won't be an isomorphism, right? I mean, K can be any field; it could be finite or infinite, but certainly, for example, if G is a finite group and K is an infinite field, like the real or complex numbers, then certainly this will not be an isomorphism of groups. So. But it will always be true that for any element in G, this matrix is invertible. That's always true of any representation. I mean, this is a group itself, right? The invertible linear transformation. So your map, so it has to have inverses. So everything will have an inverse. What about representations? Yeah, over modules or rings instead of vector spaces. So that I actually haven't studied a lot myself, but of course we can. Just consider like a G action on some R module M, where now we just ask. So again, the underlying set, instead of being a vector space, is a module, and we just ask that this is R linear. So, yeah, it's just the exact same conditions up above. It's just the exact same conditions up above. But of course, I mean, so these things also come up in nature and are important. Like, I think, in group cohomology, we have things acting on Z modules. We have G actions on Z modules. Like, that's an important thing that arises. You can view things from that perspective. But, I mean, of course, there's always a delicate balance in mathematics of having too much or too little structure, right? If you have too much structure, things become too rigid. There isn't much to say, or there's too much data to track. If you don't have enough structure, then it's hard to say anything. In the context of representations of p-adic groups, that I don't know, actually, because yeah, I mean, sorry. Let me say one other thing. Also, like, yeah, the thing is, remember, part of our original inspiration. So again, yes, these things do come up in nature, and yes, we want to study them. But also part of the original thought process here, and to be clear, I mean, I guess this is probably anachronistic. So don't take it as like, this is a post hoc justification. I don't know, it's historically not how the field developed, but we wanted to have some sort of geometrically intuitive group action, and we wanted, the powerful tools of linear algebra. If you go to an arbitrary ring, you now lose those powerful tools of linear algebra. They still essentially hold over a principal ideal domain. Okay. But to be honest, group representations over finite fields is like hard enough already. Now, for representations of p-adic groups, yeah, I know nothing of. I'm not to say that it doesn't happen, but I haven't seen this come up at all. Like, in the representation theory I deal with, like, I'm always dealing with, well, not GLN, but some p-adic group and smooth representations into a complex vector space. And I've seen, there's also like modular representation theory, and then what's probably the most hard one. I think the theory is generally fine if you take it over like QL for like L, or maybe QL bar for L not equal to P, but then the theory gets harder if this is a characteristic P. The theory then gets much harder in this case, because now you've got like, the L not equal to P case is trivial for like, well, not trivial, sorry. There's definitely a lot of difficult things going on there, but easier topologically in a certain sense for similar reasons that go on here. It's just because like the topological construction, the topological structures for L not equal to P are incompatible. So there's not a lot of interesting things that can go on in that sense. Whereas in the L equals P case, now you've got compatible topologies on either side of this homomorphism. And so now much weirder things can happen. So, yeah. That is the lowdown on representation theory. But yeah, it's useful. It's useful all sorts of places. So yeah, as I was mentioning, something wandering traveler you might want to look into is Galois representations in particular, because that'll build off of some of your knowledge of Galois theory. Although probably you want probably you need to pair that with some algebraic number theory, I would say. Yeah. Hang on just a second. Okay. Yeah. So, where are we? What else is number theory? Representation theory. Maybe this isn't surprising given everything I've said, but it also very much goes into like the classification of finite simple groups and understanding groups. Perhaps that's unsurprising, right? The whole goal of this was to find some concrete way to study groups and to lean on the strong tools that we already have of linear algebra. So probably that shouldn't be much of a surprise. Yeah, I guess that's all I have to say about that at the moment, unless there's more questions. Yeah. Okay. What to yap about towards the end of my coffee here? Maybe a little bit about where this is going long term. So at the very end of this, I guess let's touch upon this general thing. So, how do we generalize this? We have SL2. We have our H eigenspace decomposition. And then we are somehow able to talk about how E and F act on this, translate you across this eigenspace decomposition. So how might things generalize? Because, well, yeah. So like, what happens more generally? Let's look at the case of SL3 now. So here we had a basis given by HEF, right? There's just sort of these three matrices. So what is the general pattern that we can find when it comes to the case of SL3? Well, now the dimension jumps a bit. And also the question is, well, so here we had some particular basis element, and we said we're going to take the eigenspace with respect to that basis element. So how are we going to make that choice over here? We're now in SL3. Well, again, let's think about, so maybe I'll remind you that our H was this diagonal matrix. Our X was this upper triangular matrix. And, E, this was H, this was E, this is F. So now let's think about SL3 in general. So again, these are going to be trace zero matrices, right? So I could call it H1, H2, and then this would have to be, negative H1, negative H2, for example, right? And then, well, there's no other restrictions, right? So I have like X, Y, Z here, and maybe U, V, W down here. So then, as one particular choice of basis, I could take something like 1, 0, minus 1, let's say. And possibly, so we know we can see from the diagonal that there's sort of like these the diagonal elements will be two-dimensional, right? There's really two free variables. So I could take it to be maybe these two, right? But of course, these aren't the only choices, but fairly simple choices to take. So now the question is, well, I have, these are kind of both the analogs of the matrix H I had before, but now it's two-dimensional. So which one should I take the eigenspace of? And then, of course, I have all of the, I have the upper diagonal matrices. So, now there's sort of like three things that kind of play the role of E, and there's three things that kind of play the role of F. How am I going to control both of these at the same time? Well, remember that if you have some, if you have a collection of commuting operators, then they can be simultaneously diagonalized. And one of the things about the elements in the space, so you'll notice, much like, so I don't know, maybe I'll call this H1, I'll call this H2, capital H. You'll notice that these matrices, they commute with each other. And so we should get then, so it still makes sense, actually. There's no need to choose. We simply take the commuting, we simply take this whole span and we look at some sort of simultaneous eigenspace of these. But also, I guess we need to say something about what do we mean by eigenspace, because that also becomes a little bit more complicated. What do I actually mean by that? Well, I'm going to say that V is an eigenvector if there exists, let's say, an alpha eigenvector. So now it's not just a matter of being a number, because, again, in the previous case, we were just looking at one matrix. But now alpha, instead of just being like a scalar, it has to be a linear functional. So a linear map from, sorry, I should have said little h is going to be the span. I'm working with complex numbers for now, but little h has to be the span of these two things, such that, for all v, in the so this will be like the alpha eigenspace, or maybe I'm getting ahead of myself here. I'm jumping to a special case. We have what? We have that the action of anything in H is just given by the action of this, right? For all H in little h here. So that's how we're going to generalize that idea. And maybe just before I end the stream here, if we look back, look back all the way. One of the things that we made use of in these eigenspace computations, right? I deliberately tried to do this computation here a little more abstractly, where we saw that E took an alpha eigenvector to an alpha plus 2 eigenvector. I did it a little more abstractly, where the main tools I used was just the Lie bracket in GL of a vector space, or in particular the matrices for the vector space over SL2, and I used the Lie bracket of SL2 itself. So if we can find and sorry, one other part was in particular. So not only did I use those facts, but I used that we had these nice relations between these basis elements. So we had some sort of nice relation in this particular kind of basis, and in fact, that actually corresponded to a particular eigenspace decomposition, and which eigenspace decomposition, that was a very sort of special one called the adjoint representation, right? So this was exactly the case where we had SL2, which was given by SL2 acting on GL of SL2, right? So somehow we got a representation that sort of came inherently from SL2 itself. And so that is also part of the generalization, the more general game that we're going to play here, is that we're going to look at, we're going to take an arbitrary Lie algebra. We're going to find some subalgebra H, which is which has the property that, for all H1, H2 in H, the Lie bracket is 0. So by the way, we call this an abelian subalgebra. So we say that H is abelian. We're also going to try and make this as big as possible. So we also want it to be a maximal abelian Lie algebra. I guess the idea is we're trying to just sort of get, because again, it's this problem of like, in SL2 we have these two matrices, and it's like, which eigenspace do we choose? Well, why choose one, right? We know that they commute with each other. Why not take the simultaneous eigenspace? So if there was some other vector that floated out there that bracketed with 0 with everything in H, let's just toss that in and find the simultaneous eigenspace of everything. So we're going to take that, and then we're going to use the sort of special representation, the adjoint representation of G acting on itself, where, you know, an element X gets sent to the linear transformation by bracketing by X on the left. And we're basically going to look at, you know, special eigenvalue decompositions or eigenspace decompositions here. And in the same way that we were able to then lift that to more general representations for SL2, this is going to work for Lie algebras more generally. Okay, so I think that's going to do it for today. Thanks, everyone, for joining me. Now you know a lot more about Lie algebra representations, so go prove some theorems.